The country of Audonia has only 3-cent and 5-cent coins. Is it possible to make change for $1 using 31 coins? Okay, let's think about what 31 coins means. So if we have 31 coins, that is an odd number of coins. And we know that we get to an odd number by adding an even number to an odd number. That's the only way we get an odd number. So if we're using 3-cent and 5-cent coins, we know that we're going to have either an odd number of 3-cent coins that we're going to be adding to an even number of 5-cent coins, because remember we have 31 coins altogether. So what does that mean in that case? If we have 3 times an odd number, well, we know that an odd number times an odd number is an odd number. And then we're going to be adding that to 5 times an even number. So an even number, or an odd number times an even number, is an even number. But when we add an odd number to an even number, we get an odd number. And $1 is even because it is 100 cents, so that wouldn't work. What happens if instead we add an odd number of 5 cents to an even number of 3 cents coins? Well, once again, 5 times an odd number is an odd number times an odd number, which is odd, and we are adding that to 3 times an even number, which an odd number times an even number is even. Once again, we are adding an odd number to an even number, and we get an odd number. So once again, it is impossible for us to get to exactly $1 using 31 coins that are made up of 3-cent and 5-cent coins. So the second part of the question wants us to figure out what other values we can't make change for using only 3-cent and 5-cent pieces. So here they give us some examples. They say, well, we can't make 1 cent using only 3-cent and 5-cent pieces. We also can't make 2 cents or 7 cents. Well, why is that? Let's see what we can get to using 3-cent and 5-cent pieces. So the best way to think about it is we can basically make multiples of 3 cents and multiples of 5 cents and combinations of the two of those. So for 3 cents, what are some multiples of 3 that we know? Well, 3, 6, 9, 12, 15, and so on. What about 5 cents? 5, 10, 15, 20, 25, and so on. So you can see now how with these 2 coins, there's no way that we can get to 1. There's no way that we can get to 2. What about 4? We can't get to 4 either. We would have to add 2 and 2. We'd have to add 1 to 3. We don't have a 1-cent piece, so we can't do that. 6 is easy because it's 3 twice. What about 7? 7, we'd have to add 2 to 5, or we would have to add 1 to 6. There's really no other way, so we can't reach 7 either. So let's think about how we can work this out in a general form. Notice that for multiples of 3, we can express them as 3k. So all the numbers here that you see, 3, 6, 9, 12, they can all be expressed as 3k, where k is some integer. So for 3, k is 1, for 6, k is 2, for 9, k is 3, and so on. So what do the numbers that we can't get to using just multiples of 3 look like? Well, they would be the numbers that are in between So for example, we can't get to a number that looks like 3k plus 1 because that's not going to be a multiple of 3. What about 3k plus 2? Well, we can't get to that either because once again, that's not a multiple of 3. What about 3k plus 3? Well, that's a multiple of 3 because here we've got another 3, and that's basically equal to 3. We can write that like 3k plus 3 times 1, and we can factor that into being 3 times k plus 1. So once again, that's a multiple of 3. So the only numbers that we can't get to using multiples of 3 are those in between, those that are 1 higher than a multiple of 3 or 2 higher than a multiple of 3. We can also write this as 3k minus 2. Because when you think about it, if it's 2 less than a multiple of 3, it's just 1 higher than the previous multiple of 3. And we can write this one out as 3k minus 1 for the same reason. So just to give you an example, let's imagine that 3k plus 1, let's make k, if k is 2, then 3k plus 1 is 3 times 2 plus 1, which is equal to 7. And using the same number, 3 times 2 minus 2 is equal to 4. So you see they're 3 apart. 4 is 1 higher than 3, and 7 is 1 higher than 6. So neither of those work as multiples of 3. Okay, so with that stuff in mind, let's try to figure out what we can and can't reach using multiples of 3 and multiples of 5. So this is going to take a bit of figuring out, but let's start off with 3k plus 2. So we know that this is one of the numbers that we cannot reach using multiples of 3. That is the same as saying 3 times k minus 1 plus 3 plus 2. So why does that make sense? Well, imagine that how these two would be the same. Let's think about the example that we used before where k was equal to 2. So if k was equal to 2 here, we would have 3 times 2, that's 6, plus 2, and that's 8, which is the same as 3 times k minus 1. If k is 2, then that would be 3 times 1, which is 3, plus 3. So we're adding that multiple that we took away over here, we're adding it outside. And then of course we're adding the 2 back on to make it into 8. So now we can rewrite that as 3 times k minus 1, and we can combine the 3 and 2 into a 5. So what do we have there? A number that we could not reach using multiples of 3, we now can reach by adding a 5, and we're allowed to use 5-cent coins. So now we can get to that number. What about when we have 3k plus 1? So another way we can express that is by saying 3 times k minus 3 plus 3 times 3, and then we're adding that 1 again. So why does that make sense? I'm going to do a little example just to show you guys where that comes from, just to be clear. So for the sake of this example, let's make k equal to 4. We'll work with that. So I'm going to write 3 times 4, I'm substituting 4 for k, plus 1 is equal to 3 times 4 minus 3 is 1, plus 3 times 3 plus 1. Okay, so what can I do next? I can multiply 3 times 4 on the left side. That makes 12 plus 1, and that's equal to 3 times 1 is 3 plus 3 times 3, which is 9, and then I'm adding that 1. So if you look at it, you can see how here I was multiplying 3 times 4, which is 12, and I just took the two of those factors of 3, two of those multiples of 3, I took them out, actually 3 of them. I took 3 multiples of 3 and I put them outside of the brackets. So here I'm multiplying 3 by 1, and then here I'm multiplying 3 by 3. I end up with the same thing because 3 plus 9 comes to 12. And if I add everything together, you can see that on the left side I get 13, and on the right side I also get 13. So it comes to the same thing, and I just wanted to show you guys why it made sense to take a bunch of multiples of 3 out of the bracket, and we're going to see how that's going to help us get to the solution, but I just wanted to show logically why we could do that. Okay, so I'm just going to rewrite that line so that we can see what we're working with. So 3k plus 1 is equal to 3 times k minus 3 plus 3 times 3 plus 1. Okay, so 3k plus 1, and over here on the right side I'm going to rewrite the first part of the equation, so 3 times k minus 3, and then I'm going to work out the right side. So I'm adding 3 times 3, which is 9, plus 1, and that makes 10. Okay, and what is 10? So 3 times k minus 3. So I know that whatever I have going on here is a multiple of 3 because it's being multiplied by 3. And then I'm adding 10. What is 10 but 5 times 2? It's a multiple of 5. So I'm basically covered. All the multiples of 3 can be reached with 3 times a multiple of it, or 3 times any number. All the numbers that are 1 above or 2 below a multiple of 3 can be reached by adding a multiple of 5, and all the numbers that are 2 above or 1 below a multiple of 3 can also be reached by adding 5. So basically, I can get every number except for the ones that I found at the beginning because they are too low. So those initial numbers, 1, 2, 4, and 7, I can't get to because I need something smaller than multiples of 3 and 5 in order to make them work. But I have just proven that I can get to everything else using some combination of 3s and 5s.